We want to solve x squared minus 4x all over x squared minus 2x minus 15. When does that equal 0? And then we'll solve when is that less than 0. The first thing we want to do is factor both the numerator and the denominator. We'd factor out an x, and then we'd be left with the quantity x minus 4 in the numerator. In the denominator, we're going to have the quantity x minus 5 times the quantity x plus 3. Now we do have to factor the numerator and denominator to make sure there are no linear factors that cancel, because then that would be a hole in the graph as opposed to an x-intercept, which is what we're trying to find when we set a function equal to 0. Since none of these factors are going to cancel out, we can now go ahead and set the two factors in the numerator equal to 0, because that's when a quotient equals 0, when the numerator equals 0. So we have x equals 0 and x minus 4 equals 0. So we have x equals 0 and x equals positive 4. Those are the solutions to the equation. Now, how do I go about solving the rational inequality? Well, we could graph and look at the graph and see when is that less than 0 or below the x-axis, but it's not really feasible to graph an entire rational function when instead we can do a sign chart or a sign analysis. And we have half of the information that we need so far. We have found the zeros of the function, but we also need any places where the function is undefined. Since we already factored the denominator, we know that the function is undefined at positive 5 and negative 3. So we set x minus 5 equal to 0, that's where we get positive 5, and x plus 3 equal to 0, that's where we get negative 3. So these are places where the function is undefined. And these values over here were zeros of the function. So we're going to take all of those values and we're going to put them on a number line to do a sign analysis. So we have negative infinity to infinity, and we'll go ahead and plot negative 3. That's a value where I'm undefined, and so graphically there's going to be a vertical asymptote there. So I'm going to draw this dotted line, dashed line, to represent that, or sometimes people write a little u above negative 3 to indicate undefined. Then I have 0, well that's a 0, so I'm going to put a little z. And then I have 4, which is another 0, so I'm going to put a z. And then I have 5, which is another undefined location or vertical asymptote. Now I'm going to go ahead and pick some test values, which are going to be representative of each of the intervals that we've created here. So between negative infinity and negative 3, I'm going to pick a test value in here, negative 4. Lots of options, but negative 4 is a nice integer in there. Between negative 3 and 0, I'll go ahead and pick negative 1. Between 0 and 4, I'll pick positive 1. Between 4 and 5, I'm going to pick 4.5, 4.5. And between 5 and infinity, I'm going to pick 6. And what we do with these test values is we substitute them in to the original function to see whether the output is negative. We want the output to be less than 0 or negative. Well, the original function was unfactored, but we can choose to substitute it into the factored version because they're equivalent. And it's easier to do a sign analysis on the factored version. So I'm going to substitute these values, these test values, into x times x minus 4 over x minus 5 times x plus 3, all of those factors. And I'm going to do a sign analysis. So I'm going to think about taking negative 4, plugging it into x. Well, that's a negative. And then negative 4 minus 4 into the second factor, that's going to be another negative. All over in the denominator, negative 4 minus 5 is negative. And negative 4 plus 3 is negative. So in the numerator, a negative times a negative is a positive. In the denominator, I get another positive. Overall, this interval is positive, and so I don't want this interval. So I need to now check negative 1. So negative 1 is a negative value. Negative 1 minus 4 is a negative value. Negative 1 minus 5 is a negative value. But negative 1 plus 3 is a positive value. So the numerator is positive, but the denominator is negative. So overall, this is a negative interval. So it's a little bit, time consuming, but not too difficult. We're just figuring out the sign of each factor. So we have 1, that's a positive. 1 minus 4 is negative. 1 minus 5 is negative. And 1 plus 3 is positive. So we get a negative in the numerator, a negative in the denominator. Overall, that's positive. 4.5 into x, that's positive. 4.5 minus 4, that's positive. 4.5 minus 5 is negative. And 4.5 plus 3 is positive. So it's a lot quicker than, let's say, substituting 4.5 into this original function and then squaring it and doing all the computation. And so overall, let's see, we get a positive in the numerator, a negative in the denominator, and overall that's a negative, so I'm going to want that interval. And then finally, when I substitute in 6, I'm going to get a positive. 6 minus 4 is positive. 6 minus 5 is positive. And 6 plus 3 is positive. So a positive over a positive is a positive. All right, so we don't want every other interval. Just as a heads up, that doesn't always happen. It doesn't always alternate. But we do want these intervals here, these negative intervals from negative 3 to 0 and from 4 to 5. So in interval notation, we are going to express our answer as negative 3 to 0, not including negative 3 because that's a vertical asymptote, but also not including 0 because that's where I'm equal to 0 and I want to be just less than 0. And everything from 4 to 5, also not including 4 and not including 5. Now let's solve the rational inequality 5x minus 10 over quantity x minus 3 squared. When is that greater than 0? Well, I can factor the 5 out of the numerator, so I have 5 times the quantity x minus 2 over x minus 3 squared. When is that greater than 0? So we set the numerator equal to 0 to find zeros. Well, that's just setting x minus 2 equal to 0 since 5 can't equal 0. So I get x equals 2 is a 0. And then I set the denominator x minus 3 squared equal to 0. Well, that's just x minus 3 equals 0, or x equals 3. That's a place where I'm undefined. And I put those two numbers on my number line. So I have positive 2, that's a 0, and positive 3, that's somewhere where I'm undefined. And I pick some test values. So let's say 0 between negative infinity and 2, 2.5 between 2 and 3, and 4 between 3 and infinity. And let's substitute those into the factored version. So 5 times the quantity x minus 2 over x minus 3 squared. Well, this is actually really nice because 5 is always positive, so I don't have to think about that. And the denominator is always positive as well because we're squaring x minus 3. It doesn't matter what we plug in. If we square it, it's positive. So I'm really only substituting my test points into the factor x minus 2. So here, if I plug in 0, x minus 2 is negative. If I plug in 2.5, 2.5 minus 2 is positive. And if I plug in 4, 4 minus 2 is positive. I wanted greater than 0 intervals, positive intervals. So I don't want this interval. I want these two intervals here from 2 to 3 and from 3 to infinity. So in interval notation, I'm going to say my answer is open parentheses around 2. I don't want where I'm equal to 0. So open parentheses around 2 to 3 and open parentheses from 3 to infinity.